Everyone, I hope you're all healthy and well. Thank you for joining us again for the next talk in our Golden Webinars in Astrophysics series. My name is Evelyn Johnston. I'm a postdoctoral fellow at the Institute of Astrophysics at the Pontificia Universidad Católica de Chile. And together with Thomas Putzia, a member of the faculty and head of outreach, we have organized this series of webinars. First of all, we'd like to thank you all for the overwhelming response and encouragement we've received. We really appreciate your comments and suggestions, so please keep them coming. We will continue to bring you these talks in the original English and simultaneous Spanish translation without any registration fees. This has been made possible by the generous support of the Center for the Astrophysics and Related Technologies, also known as CATA for the Spanish acronym. As many of you may be aware, today is the International Asteroid Day and marks the anniversary of the Siberian Tunguska event, which took place on June 30th, 1908, and which was the most harmful known asteroid-related event on Earth in recent history. The aim of Asteroid Day is to raise awareness about asteroids and what can be done to protect the Earth, its families, its communities, and the future generations from such a catastrophic event. But let's not think about imminent impacts today. Instead, we've invited Mike Brown, a professor at the California Institute of Technology, to tell us about the icy asteroids in the outer solar system. But first, though, we'll give a brief introduction as to how the webinar will be run.
So, as you know, we have arranged for simultaneous language interpretation provided again by our Patricia Gonzalez, who is Director of Serendipia Soluciones, who will be translating for us in both English and Spanish and English directions. So on your devices, you can switch between the English and the Spanish channel using the interpretation button, which should be at the bottom of your Zoom window. So we had some complaints that Zoom is not working well in the browser and on Linux machines. So this seems to be a bug, and we apologize for this. So there is no way how to solve this with the current states of the Zoom. We've also heard that a few participants had problems with the original language. Both channels were overlapping. So one solution to this is just to simply log out and log back into the session. If you have any questions during the talk, please type them in the Q&A window. So all viewers will be able to upvote questions and then comment on them as well. So naturally, the best questions will hopefully surface to the top. And we have a team of astronomers and journalists in the background who will be monitoring the questions and then select simply the best ones for the discussion after the talk. The talk is expected to last 45 minutes, maybe a little bit longer, and we will have time for questions at the end. The questions from the audience will be selected only from the Q&A window, so please do not type them in the chat and not from the live stream on our social network platforms like YouTube.
So before we begin, I'd like to briefly introduce the other panel members who've joined us today. So we have myself and Thomas, we have Patricio Gonzalez, who is acting as our interpreter, and of course we have Mike Brown, who's going to be giving us the talk. We also have Sergio Best, one of the students in our department, and one of our postdocs, Giuseppe Dago. We're also pleased to say that we have John Hibbard as one of our guest panelists. So John is a scientist at the NRAO in Charlottesville. And as usual, we have our team of Q&A managers who are Ricardo Acevedo, Daniela Fernandez, and Carol Rojas. So it's our pleasure today to introduce Professor Mike Brown as our speaker this week. So Mike studied physics at Princeton before moving to the University of California in Berkeley for his PhD, which he completed in 1994. Following his PhD, he was a Hubble postdoctoral fellow at the University of Arizona and then at Caltech, before joining the faculty at Caltech in 1997. Since 2008, he has held the position of the Richard and Barbara Rosenberg Professor of Planetary Astronomy within Caltech.
Mike studies the most distant objects in our solar system with the aim to better understand how planets have formed. Throughout his career, he has discovered dozens of dwarf planets and is responsible for the demotion of our beloved planet Pluto from the status of planet to the status of dwarf planet, as many of you know, resulting in the nickname of Pluto Killer. In 2010, he published a book entitled How I Killed Pluto and Why It Had It Coming. So everyone should buy this. It's a great read. Part of this current work is searching for the elusive planet 9, a hypothesized body that is possibly the 5th largest planet in our solar system. During his distinguished career, he received many awards, including the Kavli Prize in Astrophysics in 2012. So now we would like to hand over to Mike to tell us all about his work on the icy asteroids and what they can tell us about Planet 9. Mike, take it away, please.
Thank you very much, Thomas. Thanks to everybody for inviting me here today, and thanks for all the audience for showing up. This is I'm pretty excited to have this opportunity to give a talk in Chile, which I've never had a chance to do before, and do it here from the comfort of my own home, which is a little bit strange. And I'm actually extremely excited and want to thank Patricio for being here interpreting. I've never actually had somebody interpret, and if I tried to use my Los Angeles Spanish, you guys would laugh at me and it would not go very well. So glad he's here too. So I'm going to tell you some stories today about how we're using the icy bodies at the edge of the solar system. This is, of course, Asteroid Day. So I'm talking about these asteroids, these icy bodies at the edge of the solar system, the Kuiper Belt, we call it, how we're using those bodies to look out into space and realize, we think, that there is a giant planet out there still to be seen. So this story starts, when I share my screen correctly. Here we go. I practiced making that super smooth. It still didn't work. This story starts really as long ago as you can imagine people looking up at the sky. People looking up in the sky noticed that there were objects in the sky that moved. There were all the stars. They couldn't see galaxies, but the stars were always in the same place, night after night after night after night, moving across the sky, but in the same place. And then there were these bright objects that were wandering across the sky, the planets, the wanderers. And the most distant of these was, of course, Saturn. And if I had been giving this talk in I don't know, 1700, there would be no other known things out beyond Saturn. I could talk about the most distant planet in the solar system, and we knew them all. And it wasn't until William Herschel was carefully scanning the skies in 1792 that he realized that there was something out there that nobody had ever seen before. That looked, at first when he saw it, it just looked like a little fuzz ball. It didn't look like a star. He didn't really quite know what it was, but he went back and looked the next day, and it moved. And that is the essential property of something that's a planet in our solar system, or anything in our solar system. It's moving across the sky. He didn't really know what it was, because I don't think anybody had ever actually thought very hard about the possibility that there were other planets in our solar system to be found. And so he spent a while trying to convince himself that it was something else. He thought maybe it was a comet. He just didn't really know what it is. But finally, people realized that it was actually a planet, or it seemed like a planet. And people, asked him what he wanted to name it. In fact, he proposed that it be named George. True story. He wanted to name it after King George, and I think get favors from the king at the time. That name didn't stick. We all now know this as Uranus. But even right after the discovery, even though people knew it was quite far away, people didn't know for sure whether it was a planet or maybe it was a comet. Comets. Comets are these things that come close around the sun and then go zooming out much further away, as opposed to planets in those big circular orbits. And people couldn't figure out at the time which it was. It took until about 1820 when a French astronomer, Alexis Bouvard, realized that he could track the orbit of Uranus for long enough period of time that he could then find it earlier than it had been originally been discovered, and he could construct a complete orbit for the whole thing. So he wrote this whole book with this crazy name. The name's not too crazy. Tables of Jupiter, Saturn, and Uranus. His titles are pretty crazy. Bouvard is he's a Royal Legion of Honor, member of the Academy Royal of Sciences, Bureau of Longitudes. He's got all kinds of titles. I need some of his titles. Those are pretty good. But he included this one table that's perhaps my favorite table from any book published in 1821, which is right here. So first off, he used those observations he had to precisely figure out where Uranus was supposed to be, taking into account the gravitational perturbations of Jupiter and Saturn. And he wrote this whole theory with all these signs and, I was going to say sines and cosines, but it only has signs on it, all these signs in it and all these different terms to see where the planet was. And then he went back and looked at all the old observations that he realized were of Uranus, and he made this other table on the other page showing how far off the observations were. Here were the observations at the time of discovery. Here in the 1790s were pretty close. They were a few arc minutes off, but he went all the way back to 1690, and the observations were kind of far off. Then they went off the other direction. Then they went off the other direction. Even by 1820, they were off there. Bouvard, as a theoretical astrophysicist, we all know them. We know who you are. Bouvard was convinced that his observations were perfect, and so it must be that his theory was perfect, so it must be that the observations were wrong. He told the astronomers of the day, make better observations to prove his theory correct. So the astronomers did. The astronomers spent the next 20 years carefully following Uranus in the sky, doing very precise measurements of where it was in the sky, and realized it still was not where it was supposed to be. By about 1840, it was pretty obvious that the reason that Uranus was not where it was supposed to be is that there must be another planet further out there that was tugging it along in its orbit. This is funny. It's an interesting part of the story of the eventual discovery of Neptune that most people don't realize, which is that 5 years before the discovery of Neptune, it was generally accepted that there was another planet out there. The hard part is nobody knew how to find it. So it took another French astronomer, Urbain Le Verrier, to work out the mathematics to allow him to use tables like this that showed the perturbations and the discrepancy of Uranus, to use those tables to predict a location of this new planet. He sent that prediction to the Berlin Observatory. Berlin Observatory opened the telescope that very night, the very first night, and boom, there it was. Planet Neptune was immediately discovered. This is one of the, still to me, one of the most amazing stories of sort of prediction and discrepancy and triumphant discovery in all of modern science. I think of this as the point when people started to believe that, wow, this physics thing is actually real. You can use this physics to predict new planets and actually be right about it. It was a pretty amazing thing. It was a pretty amazing thing. And also Leverrier became really super famous for having made this discovery. His statue, I'm sure there some of you have seen it. His statue is in Paris, looking straight north up along the boulevard going to the Luxembourg Gardens. He's one of only, I forget the number, 90 people, I think, who have his name inscribed in the Eiffel Tower. Pretty big deal, discovering a planet, as they said, at the point of a pencil. And so, you know what happens when somebody gets really famous finding a new planet? Everybody else wants to get in on the act. So almost immediately from the moment Leverrier announced the prediction, and it was then found in Berlin, people started predicting new planets usually using some form of perturbation that they saw in something. And in fact, some of the perturbations were still in the orbits of Uranus and in the orbits of Neptune. They didn't seem to quite fit right still. And so literally within months, there was another prediction of another planet further beyond Neptune. I went back and counted as best as I could over the last 150 years. There have been something like 25 separate predictions of new planets beyond Pluto. And in 25 cases, the astronomers have always been wrong. The most famous of these wrong predictions is the one that almost seemed right for a while, came from Percival Lowell, who was an astronomer who lived in Boston at the time, and he founded an observatory, the Lowell Observatory in Arizona, to look for what he called Planet X. Planet X, people sometimes think Planet X stands for either 10 or unknown, and it's a generic term. It's not. Planet X was a very specific planet for which Lowell was looking based on what he thought were the perturbations to Uranus and to Neptune. Uranus and Neptune still didn't seem to quite go around the sun they were supposed to, and Lowell wanted to find that Planet X. He founded the Lowell Observatory. He set in motion this survey to look for his Planet X, and he made a prediction. Planet X was huge. It had to be huge. It had to be huge to take into account, to cause those perturbations that were being seen in Uranus and Neptune. The search started in 1929, I think, were some of the first observations, and the first successful discovery came from Clyde Tombaugh in 1930, when they discovered this tiny, tiny, tiny little point of light in the sky, which is now known, of course, as Pluto. If you look at the New York Times headline for the day of the announcement of the discovery of Pluto, it says, ninth planet discovered in the solar system, predicted exactly as predicted by Lowell, and it is possibly the size of Jupiter. This is wrong by about a factor of 250,000. Pluto is a tiny, tiny little thing that has much less mass even than our own moon, and it turns out has no effect whatsoever on the orbits of Uranus and Neptune. People didn't know that at the time. They thought it must be this big thing, and they said, well, if it's big, it must be a planet, and that really is why it stayed a planet for all those years. It was just because of that mistake from early on, that coincidence that it happened to be found when astronomers were looking for a planet, but it wasn't the planet for which they were looking. Astronomers continued to look for these things that were perturbing, and they really continued until about 1990, around 1990, 1992, when the Voyager spacecraft finally flew past Neptune for the first time. And by flying past Neptune, it had recently flown past Uranus. By flying past those two planets, it gave a very precise measurement of the mass of those two planets. And when astronomers finally knew the masses of those planets correctly, and they put those into their calculations of gravitational perturbations, they realized everything was exactly where it was supposed to be. There was no evidence whatsoever for anything else in the solar system. The idea that there was a planet X was dead, gone. There's nothing perturbing the orbits of Uranus and Neptune, at least for now. Interestingly, right about the same time, though, something new started happening, which was the discoveries of new objects in the outer part of the solar system. Let me walk you through some of those. Here are the orbits of the inner planets there in yellow. You see Jupiter, you see Uranus, you see Jupiter, Saturn, Uranus, and Neptune. You even see Pluto on its crazy orbit that goes inside the orbit of Neptune. It didn't even make sense back when we called it a planet. It certainly doesn't make sense as a planet now. If you turn them sideways, you can even see that the planets, of course, are all in their nice circular orbits in one plane going around the sun. Pluto is crazy, or at least it seemed crazy at the time, until 1992, when these other objects started getting discovered around the sun. These other objects are the objects in what we now call the Kuiper belt. These are the icy asteroids that the title talks about. And these objects go mostly outside the orbit of Neptune, but they're in this bird's nest of orbits. They have orbits that are tilted like Pluto's. They have orbits that are elongated like Pluto's. We now realize that Pluto is a perfectly normal member of this population, and that the only reason we called it a planet for all those years was just because it was the first one that was discovered. It was a bright one, not even the brightest one, but the brightest one at the time discovered. But the whole population out there is basically just a mess of bodies, mostly outside of Neptune, sometimes very far outside of Neptune. Again, everything is where it should be. Every single one of these objects that you can see on this slide is exactly where it should be based on the perturbations for all the known objects that we know in the solar system. At least at this time, there was nothing else known that couldn't be explained by the solar system. That all changed in 2002 with the discovery of Sedna. Sedna, at the time of discovery, was a crazy elongated orbit. This object takes 10,000 years to go around the sun, and that's crazy. But actually, the crazy part is not that it takes 10,000 years to go around the sun. The crazy part you can actually see right here. If you look very closely, it never comes close to anything else in the solar system. All the rest of these objects that we see in the Kuiper belt are all kind of tucked in pretty close to Neptune, sometimes go inside the orbit of Neptune. Sedna uniquely never does. That's weird. Let me tell you why that's weird. So I want to talk about how bodies originally got out into these very elongated orbits to begin with, and how maybe Sedna could have gotten there. So here's what we know. We know that if we started, and we'll just draw these really simple pictures. If we start with, here's the sun, let's say this is Neptune right now, and in fact, we'll say that there's an object in orbit very close to Neptune at the same time. That object will be going around the sun, and at some point, it'll get a little bit too close to Neptune. When you get too close to Neptune, one of two things happens. You either get kicked a little bit outward in your orbit, or you can get kicked a little bit inward. I'm going to show you a kicked a little bit outward. Kicked a little bit outward goes like this. You encountered Neptune right here. It gives you a kick, but just like what goes up must come down, if you give something in an orbit a kick, it has to come back to that same location. So you go out onto a more elongated orbit, then you come back in. Bad news, though, is eventually, if you keep doing this, you'll come close to Neptune again. So you'll get a kick again. Could go in, could go out. I'll just draw you out. Do that for a while, could go in, could go out. But the one thing that never happens, you should notice very carefully, is you get a very elongated orbit, like Sedna's. Sedna's on a very elongated orbit, but you never get an orbit that doesn't come back close to the thing that kicked you. The fact that Sedna never comes close to anything that we know of in the solar system means that nothing that we know of in the solar system could have been the thing that gave it its kick. It was the first object that we'd ever found that required the presence of something else in the solar system. At the time that we discovered it, I was pretty convinced I knew what that other thing was. I thought that the process was something like this. If Sedna were on an orbit like the one I just drew here, and well, if it hits Neptune too many times, it can get ejected from the solar system. But what if on its way, maybe out to here, a star comes by? Back in the early days of the solar system, there were a lot of stars close by. And if a star comes whizzing by, it gives a little bit of a tug on Sedna right here. So now the tug has happened here, which means Sedna has to return to right here, but can have an orbit that looks sort of like this. I was pretty convinced that when we discovered Sedna, we had basically discovered a fossil remnant of the earliest birth of the sun inside of a cluster. That was a super exciting thing to have potentially discovered. I thought the process looked more like this. Yes, it could have been that there was a planet that we didn't know about that gave Sedna an orbit like that. But what I really thought is that there were a bunch of stars moving around that's slowly jostling Sedna around, and that would lead to a population of objects that looks sort of like this. So the goal, starting in about 2003 or 4, we started this new survey. The goal was to find more of these distant objects and use those to really read the fossil record of the birth of the solar system itself, which to me was one of the most exciting prospects that I could think of. So we searched for approximately 10 years, and in that whole 10-year period of time, we found nothing, zero, no objects, not a single one like Sedna. It was quite surprising. I understand now why, but at the time it was surprising and frustrating. Luckily, some other astronomers, one of them whom used to work with me as a postdoc, Chad Trujillo and Scott Shepard, had a bigger survey running from one of the telescopes down there in Chile, and they were successful. They found an object that is called 2013 VP1112 that they nicknamed Biden, which is kind of a terrible nickname, but I can't help that one. That was theirs. Notice it too, like Sedna, never comes close to the solar system. Okay, so now we have 2 of these, and that's interesting. But was even more interesting at the time that they discovered this one is that they made what seemed to be a really strange discovery. They found Biden, but they also pointed out that all of the objects that go on these very elongated orbit, even if they come back closer to here, all of the objects that go on elongated orbits share a common property, which in orbital dynamics we call argument of perihelion. Argument of perihelion is such an obscure orbital property that most people who work in the solar system, they've heard of it. If you ask them what it really is, they probably couldn't describe it. But I can tell you very simply what it is. What Shepard and Trujillo said was that all of the objects that were really far away had clustered around an argument of perihelion of about 0. And what that really means is that they're on inclined orbits, but when those inclined orbits cross the plane of the planets, they do it at their closest point to the sun. Sounds kind of obscure. Let me show you a picture. This is what it really looks like. All of these objects have an argument of perihelion of 0. They cross the plane of the solar system when they're closest to the sun. What they really look like is blades of a fan. Blades of a fan is a weird thing for the solar system to be doing. It's a weird thing for the solar system to be doing because there's no gravitational force known to astronomers that can set up a pattern like that in the solar system. What that led to is astronomers, for the most part, ignoring this finding that these things were all aligned in argument of perihelion. At the time, actually, Shepard and Trujillo claimed that this was caused by a planet beyond Neptune. But of course, as I told you, 25 people in the past had said there's a planet beyond Neptune. They had all been wrong. People tend to not pay much attention anymore. In addition, the physics doesn't work. A planet beyond Neptune can't give you the picture you're looking at right now. So astronomers basically said, yeah, there's something wrong with the observations. I don't believe them. I actually believe them because I know these guys. They're good at what they do. And so this is the moment when I started looking at this along with my colleague down the hall from me, Konstantin Batygin, and we started looking more carefully at this, and we realized that that Shepard and Trujillo had overlooked one critical point, which is actually the critical point of the set of objects out there, which is that they're not just lined up in argument of perihelion, they're actually lined up in physical space. These are like blades of a fan. I'll show you how they're like blades of a fan, because they are all tilted the same way, but they're like blades of a fan that all go in one direction. This is an incredibly important thing. This means that there's a preferred direction. Why does this matter? Preferred directions are something that gravity can do. You can sort of see as this slides around here, you can tell that all of these objects are tilted in the same direction and that they're all crossing the ecliptic right there at about the same location, the plane of the solar system about the same location. And critically, they're all pointed in the same direction. This is great because the fact that they're all pointed in the same direction and that gravity can do this means that you can sit down and write some pretty simple equations if you know how to do it, which I don't, but luckily Konstantin Batygin does. So this is literally his blackboard at the time we were working on this. You can write these relatively simple equations of secular perturbations. Secular perturbations meaning long-term gravitational perturbations, and you don't have to really pay attention to anything here except for a couple of points. This one term is critical, cosine of omega prime minus omega or var p prime minus var p. That is a term that is proportional to the angle between a planet, a perturbing planet, and the direction of the object that it's perturbing. There's something that's a function of that angle. That means a planet can control that angle. There's a couple other things that matter. You see e's in here a lot. These e's are the eccentricity of both the object and of the perturbing planet, which tells you immediately that the perturbing planet has to be eccentric and the objects that it's affecting have to be eccentric. And you can see somewhere in here, there's masses. Mass of the planet matters. And so the effects occur more strongly with mass. Even if you don't sit down and solve this problem or numerically integrate this problem, you can at least see that there's effects that a giant planet could have. So let's, instead of actually solving this problem, let's do a numerical simulation and see what really happens. Here's what I'm going to show you, which is that a planet, a giant planet, and you can see barely, here's the orbit of a giant planet. Each one of these blue points is the orbit of a very elongated object in the Kuiper belt. And they start out uniformly distributed. I'm going to press go 4.5 billion years ago, and we're going to watch their orbits get modified by this giant planet. The giant planet's orbit, giant planet makes many, 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 many orbits over time. I'm not showing you the planet itself, just the orbit. I'm not showing the objects themselves, just the orbits, but let's watch what happens over time. First thing you notice is very quickly, many objects disappear. And that's because crossing the orbit of a giant planet is a really, really bad thing to do. We were really expecting to find all of the objects that live for a long period of time are in here, where they don't cross the orbit of the planet. Anything crossing the orbit of the planet can't survive very long. So let's watch. First thing we notice also, I'm going to pause for a second. First thing we notice is that if you're sufficiently close to the sun that you barely cross the orbit of the planet, not much happens to you. You precess, your orbit moves slowly around the sun, but you don't really get destroyed. You don't get caught. You don't do anything. So those are the ones in green. These ones in blue are the ones that are all the interesting stuff is happening. We're waiting for them to get stuck over here. Let's watch it. Here comes one. Here's one stuck, right? Nope, that didn't get stuck. This one is going to get, no, doesn't get stuck. Here's one. No, no. Okay, this one okay, so they don't get stuck over here. Every time they start to get stuck over here, they immediately disappear, which means they've been ejected from the solar system. It's bad news, but there's good news, which is the opposite of what we thought was going to happen is happening. They're getting stuck over here. All of the objects that are left after 4.5 billion years are, for the most part, in this fan that sprang in the opposite direction of where the giant planet is. This was the opposite of what we thought of at first, but then, like often happens in science, you do the simulations and you're like, oh, we should have known this all along. The reason it works this way is in some ways quite simple, is that we all know that the way something goes in orbit around the sun, it goes fast through here, slows down, fast, slows down. So this planet spends most of its time out through here. And these guys do the same thing, fast through here, slow down, fast through here. So the objects that are left are the ones that spend most of their time out here, and this spends most of its time out here. They spend most of their time really far away. When they cross the orbits, they're moving really fast. So their chances of encountering the planet are relatively low. Notice that most of the stuff got ejected. So most of the stuff didn't get lucky, so they still get ejected. If you have an object like this, it spends most of its time here. This guy spends most of his time here. They get perturbed pretty badly. So these are the ones that are left after 4.5 billion years. So let's just look for fun at what an individual object's orbit does. Here's the planet in blue, and we're going to watch how this one individual object's orbit changes over the course of 4.5 billion years. It doesn't just get stuck in one place, but you can see it kind of points in the opposite direction. It wiggles around. It kind of oscillates back and forth, but it basically stays tilted in the same direction as the planet and aligned in the opposite direction of the planet. So we can use that fact to understand where the planet is. And in fact, we now know that the planet has to be in the opposite direction of those objects that we see, and in fact, that the inclination of the planet, the orbit of the planet, the plane of the orbit has to be basically in the opposite direction of the things that we see. So we now know it works if you had a planet that is eccentric like this, on an orbit like this, it will make a population like this. And I remember when we first realized that it works, Konstantin and I were both kind of, excited to find a theory that works, but a little bit worried. As I told you, and by now 26 people had predicted that there was a planet based on something that they saw, and 26 separate people had been wrong. We were really reluctant to jump up and down and say, yeah, but 26 people were wrong, but we're right. This must be true. I would say we had good evidence, but not great evidence. So we really wanted to make a prediction as opposed to an explanation. In science, it's usually easy to come up with an explanation. It's a lot harder to come up with a prediction. One of the things we realized also is that our theory had what we thought at the time was a problem. In addition to predicting these objects that you see right here, our theory also predicted that there should be a second set of objects, not oriented oppositely, but oriented at a 90-degree angle to the planet, but also twisted in its orbit by 90 degrees. So plunging through the plane of the solar system on these crazy 90-degree perpendicular orbits, which, I thought to myself, there are no objects like this. It's weird that we keep predicting they should be here when they're not here. We spent a couple of months trying to modify our theory to get rid of those objects because we didn't see any, until I realized one day that I was just being stupid. There's a whole collection of objects that I just neglected to look at. Everybody gets their blinders on, and I was looking at these objects that are really distant, that are always beyond Neptune, and I was neglecting the ones that sometimes come inside Neptune. I neglected those because I thought, once you go inside Neptune, you're so perturbed it doesn't matter. But if you go inside Neptune's orbit on 90-degree inclined orbits, you basically never interact with Neptune. So those still preserve their information. So I remembered that they were there. We found 5 objects on these perpendicular orbits. And this is a super crude plot, but I like it because this is literally the plot that I showed Konstantin as he and I were sitting in my office. And I said, Konstantin, here's what you're predicting. This angle down here, perihelion longitude, tells you the direction that the objects are pointing. This little spaghetti wad down here is all the objects that are pointing opposite of the planet. These up here are the ones that are 90 degrees from the planet. The planet would be over here with this longitude. These are 90 degrees from the planet, and you can look at inclination. That's how they're tilted with respect to the planets of the solar system. So 90 degrees tilted and 90 degrees on either side of this thing. I was like, okay, Konstantin, let's take a look. Where are they? And the answer is, okay, here's the ones we knew about that are clustered over here. And here's the one that are perpendicular. And one here, 2 over here, don't miss these 2 over here, and 1 and all my faces are over here. I have to move. Yep, there's another one. Two of them over here. All of the ones that we found are exactly where we predicted in these locations. At this moment, we just both sat there. My jaw was open as wide as it could go. And in my head, it went from, this is kind of a cute idea that we have, to, holy cow, there really is a planet out there. I want to show you the orbits of these objects that are out there. And this was it. For me, this was a prediction that we had no idea that this theory was going to make. Totally turned out to be exactly right. One other prediction that we didn't even, or a consequence that we hadn't thought about. Remember Sedna and Biden, how they both have their orbits pulled away a little bit from the solar system? This planet does this all the time. Those orbits oscillate in and out, so it's no longer a mystery. So with one easy theory, we solved 3 problems, 2 of which we weren't even attempting to solve. That's pretty good. That's the hallmark of what I would say a pretty good theory. And that's the moment where we announced to the world, hey, we think we have really found that there's this planet out there. Planet 9 got its name at that point, and the search was on. Search is on, but of course everybody wants to know, okay, that's pretty good, but look, I can count. That's 1, 2, 3, 4, 5, 6 objects, and here's only 5 more. Come on, that's pretty low numbers. And the answer is, yeah, it's pretty low numbers. We did the statistics. We did the statistics correctly, I think, and showed that it's still statistically significant, but it's still low numbers. You'd like to know if it was going to get better. So we said, look, as we continue to observe, we will find more of these objects like this. It won't be 100%. The theory predicts that about 80% of the objects are in this direction. The other ones should be over here. And so how are we doing? The answer is we're doing pretty well. Yellow is where we think planet 9 is these days. And now we have 1, 2, 3, gonna lose count. 1, 2, 3, 4, 5, 6, 7, 8, 9. I think I counted 9. 9 off in this direction. 1 in the other direction. 10% in the other direction. Not too bad. The theory is working out as well as we could believe. In fact, kind of better than we can believe. But, you know, okay, it's still 9 and 1. Can we do better? And the answer is, yeah, we can do better. There are more predictions that we can make after the fact. We didn't even realize we were making these predictions, but are natural from this theory. And one of them is about another set of objects that we didn't even think about at the time. And these are objects that are on, this is again, inclination, the tilt of the object with respect to the solar system, and semi-major axis, the average distance away from the solar system. These little black dots are all the typical members of that Kuiper belt. This is that bird's nest of stuff. Some of them are out here. This line at 60 degrees is really the largest inclinations that any ideas on how the solar system formed can make objects. All of these objects down here make sense. We can make solar system models that make these objects. These, though, don't. These things that are really, really perpendicular or even flipped over backwards just don't make sense whatsoever. And you can see that these objects are also semi-major axis is the average distance. Perihelion here is the closest they come to the sun. They come closer to the sun than Neptune. Neptune is here at 30 AU. So they're all close to the sun, but on sort of elongated orbits and tilted. A very strange thing that nobody really had an explanation for. And we realized very quickly that even these closer in objects are a very natural consequence of planet 9. And the way they happen is, if you start an object, here's planet 9 in purple again, here's just a random object in yellow. This is one of the objects that never gets captured into those opposite direction orbits by planet 9, but sometimes it gets close. Every time it gets close to Neptune, you can see that Neptune messes with the orbit. Let's watch one happen. Come on, come on, come on. There we go. Mess with it. So Neptune, just like in those early pictures, sometimes Neptune can make it a little more distant. Sometimes it can make it a little closer. Sometimes it can pull it in. Sometimes it can push it out. Sometimes what happens is it pulls it in so close, it detaches from planet 9 entirely. When that happens, the inclination, it was always at a 90-degree inclination or close to 90-degree inclination. But when it happens, that inclination stays preserved, but the orbit gets pulled in to a much closer distance than it originally was. it makes those objects just like we were talking about. Not only does it make objects like we were talking about, but it does it in very specific regions of parameter space. It does it in the places where these green boxes are green. It does not make any objects in these white locations, hardly makes them in these gray locations, makes them in these green locations. I think the correspondence between where these objects have been found and where Planet 9 makes them is spectacular. Again, this is something that we never even thought about trying to explain or trying to predict. And it's something for which there is no other viable explanation anywhere in the solar system. This is pretty good. I would say that the theory itself was pretty good to begin with. The prediction of these highly inclined distant objects was, to me, pretty good. The continued finding of objects in the right direction, pretty spectacular. The explanation for objects like Sedna and Biden is great. And this is just kind of amazing. If you think that Planet 9 is not out there, you need entirely separate explanations for every single one of these things. I think there is none. I think there's no explanation almost for any of these other things, much less a simple one like a planet for this one particular one. Okay, so where is it? Well, I could give an entire other talk on the technical ways on how we're trying to find it. So now we know it's there, and I would say we know it's there. There is very little room for doubt at this point that there is a planet out there. So now we just need to find it. Now that we know it's there, we need to figure out how we're going to find it. I showed you that we could use the tilt of the objects and the location to do pretty well, but you really want to know how far away it is, how massive it is, and you can use that original math that I showed you to begin with. But in the end, what we've had to resort to is doing massive suites of computer simulations like that one that I showed you early on, and matching them to the data in a very detailed way. The technical details, for anyone who cares, is that we make massive maximum likelihood models. Well, we make massive likelihood models, including all the observational biases for all the objects that have been discovered, match the models with the biases, observe the models that we have, compare them, make out likelihoods to match, and then we can compare them and figure out what's going on. This is one set of likelihoods for semi-major axis, for example. So a likelihood, a high number is good, a low number is bad, and you can see that the likelihoods increase spectacularly as you get to a semi-major axis average distance of about 300 AU. We have sets of likelihoods for all the other parameters. The mass peaks very strongly at about 6 times the mass of the Earth, with an uncertainty of about 1. So I'll give you 5, I'll give you 7, won't give you 3, won't give you 10. All those parameters we have, so we have actually pretty good predictions on what Planet 9 is like and where it is in the sky. And let me show you what that means. That means that here are the planets: Mercury, Venus, Earth, Mars. Big old Jupiter in the background, Saturn, Uranus, Neptune. Good luck finding Pluto. It's one of these. Pluto is not a particularly significant object in the solar system. But if you put Planet 9 on there, it's huge. This is no, let's sit around and argue whether it's a planet or not. It's the 5th largest object in the entire solar system. It's a monster out there waiting to be found. Okay, where is it? Where is it waiting to be found? Well, the answer is, there's that same semi-major axis plot. So we took those likelihoods, again, for anybody who really wants the technical details. We take those likelihoods, we create a Gaussian process model, we run it through a Markov chain Monte Carlo, blah, blah, blah. So we get a whole sets of samples on where Planet 9 is. Strongly peaks here at 300 AU, which is interesting. We used to think it was out here at more like 700. We also used to think it was more like 10 Earth masses. We also used to think it was quite eccentric. All those things have come down. It's now closer than we thought, a little bit smaller than we thought. But one of the consequences of being closer is it's actually brighter than we thought. We used to think it was going to take some of the biggest telescopes in the world. I don't think it's going to take that anymore. Let me show you, we don't care about the inclination. Let me show you this, which is my favorite plot maybe I've ever made. This is a map of the sky. The line across the middle here is the ecliptic plane, the plane of the planets. That's a lie. The line across the sky is the celestial equator, the plane of the Earth. This line is the ecliptic plane, the plane of the planets. These two lines are the outlines of the Milky Way galaxy, plus or minus 20 degrees in the Milky Way galaxy. The colors are the probability density of where planet 9 is right now. So it is most likely in this region over here, close to the equator, more likely in the northern hemisphere than the southern hemisphere. Sorry. Not as likely over here. And the main reason for that is that it is, remember, it has an elongated orbit. That elongated orbit comes closest to the sun right here, which means it's going faster. It's further from the sun out here, which means it's going slower. The other thing that you can see on the slide is the predicted brightness for planet 9 at these different locations. You can just kind of read up from this location to get, oops, didn't do that. Read up from this location to see the predicted brightness. And so you can likewise see that down here, if it were in the southern hemisphere, it would be brighter. Northern hemisphere, not as bright. So now we know where to go look. Let's go find it. The other thing is we know is in a lot of locations, it's really super bright and should have been found already if it's any of these brightnesses. There are several surveys that have been done that are quite complete to 20th magnitude in both the north and the south. And the one that I'm going to show you that it's pretty good is complete to about 21.5. That's the Pan-STARRS survey. The Pan-STARRS survey, I'm not entirely sure I believe that it's been analyzed completely yet, so we're still going through it right now. But if you believe that the Pan-STARRS survey is good to 21.5, you really knock out almost everywhere, certainly much of the south, although I cheated because Pan-STARRS doesn't go quite far enough south, so I should have left some of that in. But some of the other stuff have done that too. There's a little bit of parameter space left in the south. Most of that parameter space left is really up here, and bad luck, y'all. It's all in the galactic plane. It's embarrassing to say that one of the easiest excuses for not finding planet 9 is to say, oh, well, it's just in the galactic plane. It's also the place where we predict that it actually is in the galactic plane. This is the most likely location. We've done a systematic survey of these locations using the Subaru telescope up here on Mauna Kea, and we've ruled out basically these regions. So where should you look? Well, this region down here is being surveyed really nicely by the dark energy survey that's happening from the Blanco telescope in Chile. So I think they've actually analyzed all these data and it's not there. I really think the places for it to hang out still are up here in the north and a lot of it in the galactic plane. So that's where we're currently looking. I am still willing to believe that it's going to be found before we find it on a telescope like the Subaru telescope. I actually think that it's as likely as not to be found in data that have already been taken, in archival data. Do you know that every major object that's been discovered in the solar system was seen before it was found? Way back at the beginning, we talked about Uranus. Uranus had been seen nearly 200 years before its first discovery. Neptune was the same way. Neptune had been seen by Galileo himself. Pluto was imaged even 20 years before its discovery. Eris, the most massive object out there in the Kuiper Belt that I discovered in 2005, we eventually found it in images, photographic plates taken back in the 1950s. The sky has been looked at many, many times. I think Planet 9 is going to be the same way. I think it's more likely that Planet 9 is found in archival data than it is in a telescopic survey. May not be true. If it really is as faint as some of these, I think we're going to have to go to there. So we're hot on the trail. I end all of my talks by saying we're just about to find it. Stay tuned. We're going to find it like in 6 months. I've said this for 4.5 years now, so take everything I say with a grain of salt. But I just want to end with where we started at the beginning, which was, I should have shown this again, which was this great, if I could go back if I can go back this fast, this great poster that was made early on for our thing, which is, of course, I don't know if any of you have seen this Plan 9 from outer space, world's worst movie, well known, but it was made in the late 1950s, Ed Wood, and it was prescient in many ways. Which is one thing is if you look at the graveyard scene, they were digging up zombies. Let's go see if we can find the graveyard scene of the zombies, and look in really closely at what they were doing in that graveyard scene. You have to look back, and they were actually, I think at the time, even then, burying Pluto, because they knew even back in the 1950s that it was bound to not be a planet very soon. Okay, so that part's not true, but it's a good story. And I really want to thank everybody for being here. It's fun to see that there are like more than 300 people have been sticking around through here. I'm pretty convinced. If you're not convinced that Planet 9 is real, I want to hear from you. You think that Pluto's a planet? Yeah, I don't really want to hear from you. It's just not a planet. You're just gonna have to get over it. I'm happy now to take some questions.
Wonderful. Thank you so much, Mike. This was a great journey through the history and evidence for and against Pluto and for Planet 9. And there are plenty of questions in the Q&A. So
bring them on.
Before we go into the Q&A, is there any question from the panelists?
Sergio has raised his hand.
Oh yeah, that's right. Sergio, go for it.
Hi, first, thank you for your talk. It was really interesting. I wanted to ask about the orbit of Planet 9. Has it always been the same shape throughout the history of the solar system? I mean, like, does it precess in your model?
Yeah, so it's far enough away from the sun that it's not interacting with the other planets, and so it's the shape of the orbit stays the same the whole time, but it certainly precesses. And interestingly enough, Planet 9 carries about the same amount of angular momentum as the other planets put together, just because it's so far away. And so Planet 9 has actually precessed the inner planets. I call the first 8 planets the inner planets. Planet 9 has actually precessed the entire inner planets, and it has not precessed the sun. So it is possible, although we used to be more excited about this. I don't think it actually works out in detail. So Planet 9 will precess the orbits of the inner planets, tilt them and precess them, but not precess the sun. So to us, it looks like the sun is tilting due to Planet 9. The sun is, in fact, tilted compared to the plane of the solar system. I think the numbers don't work out. When we thought Planet 9 was bigger, the numbers worked out better, but now it looks like it's not quite true. But so Planet 9 is precessing everybody else.
So one obvious corollary question would be like, who put Planet 9 in this weird orbit in the first place, right?
Yeah, so that's the great question. I have 2 answers to that, and the answer one is our theory for the existence of Planet 9 is agnostic to how it got there. So we don't know, is what I'm saying. But we have ideas, and so everybody likes to make up stories. So let me make up some stories for you. I think the most likely way it got there is exactly the process that I first tried to describe for Sedna, which is that I think it is a giant planet core that failed to accrete a giant planet mass that formed in the Uranus-Neptune region, got a little bit too close to Jupiter, Saturn, got on an eccentric orbit, and this had to have happened early when we were still embedded in a cluster of stars, and that cluster of stars would have given it slight perturbations and left it into the orbit that we see today. So that's one possibility. People have suggested that it could be captured, which is certainly true. You can imagine a star going by that had a planet, and in a 3-body interaction, we're left with that planet, and the star goes off. The probability seems low to me, but it makes for some fun Hollywood movies currently being talked about, which is that like a planet with a moon around it with a civilization is living around the star, and it suddenly gets stripped off and it's left at the edge of the solar system, and they have to go into the inner solar system and inhabit that fun little green planet that's right there. People have been talking about this movie. I'm not making this up. So that's possibility 2. And possibility 3 is it actually formed out there. Traditionally, we don't think there's enough mass for that to have happened. But our abilities to predict outcomes of planet formation have traditionally been terrible. So I guess it's not impossible. I still like the first possibility. It's a very natural consequence of everything we think we understand about planet formation. So I like it best, but it doesn't mean it's true.
Okay. Before I go on with my questions, I give the platform to Giuseppe, who has his hand raised in the chat. Giuseppe, go for it.
Yes, thank you, Thomas. Thank you, Mike, for your mesmerizing talk. And I would like to know, once you observe one of these high inclined orbit planets, how do you recognize that it is actually bound to the solar system? So how many points do you need? Do you rely only on astrometry? Which kind of techniques do you combine?
Yeah, it's purely astrometry at that point. So it really is. We detect the excuse me. We detect the object, and at the moment of detection, you see it moving, and maybe you come back a day later and you see how far it's moved. That gives you some very limited information that basically tells you the heliocentric distance and the inclination, the tilt with respect to the sun. And really, you don't know very much else. It could be pretty close, but on an eccentric orbit. It could be further away on a different eccentric orbit. It could be not bound. You don't know. So you really have to do a lot of astrometric follow-up to really get the orbit down well. Traditionally, that's meant getting it from you discover it, and then you need to detect it maybe a month later, and then a month after that, and that gives you a good enough orbit that you can find it a year later. Once you found it a year later, the orbit is down pretty good because you've seen that motion for the whole year, but you really need all those follow-up. These days with better astrometry, you can sometimes do it more quickly, but you need weeks to months to years to get a pretty good orbit.
And do you often mine back into old data sets?
Oh yeah. So this is what we do all the time now. So we don't do it as much for these distant objects that we find now because they're pretty faint. But when we first were doing the surveys for the large Kuiper Belt objects, we would find something like Eris and Sedna, and we would immediately start going back into old databases. This is how we know that these things were found so far back. So Sedna is a great example. Sedna we discovered in like November of 2002, and didn't get our first confirming observation for about 3 weeks. And then we had, from that 3-week baseline, we could go back about a year and look in a pretty broad area for where it might be. And we did. We found observations from a year earlier from a near-Earth asteroid survey. And once we had that, we could go back another year. And finally, we found it back in, I think the earliest we found Sedna at that point was a couple years earlier. But that made it from, usually it would have taken maybe 5 years for Sedna. So we got it back very quickly. So this is a very important thing to do whenever we find these things.
Thank you.
So I've got a few questions here from the audience. So the most upvoted question is by Jorge Quadra. If Pluto was supposed to be Jupiter-sized, wasn't its dimness very unexpected?
Yes, that's a great question. So this shows you, I think, one of the ways that science can fool itself, but it also shows you the science is self-correcting. People were looking for a planet, and they found something and assumed it had to be the planet. So even though it didn't quite fit right, people bent their ideas to fit their expectations. I have to say that even Clyde Tombaugh, who discovered Pluto, was a little bit dubious. He spent the next maybe 20 years continuing his survey. He found Pluto within the first year of his survey. He spent the next 20 years continuing the survey of the sky because he was not convinced that that was the planet for which he was looking. He still thought that there must be something big out there perturbing Uranus and Neptune. This was before we knew that the masses of Uranus and Neptune had been wrong. But it's a great question because it shows you how our perceptions of what we're looking for can really influence our interpretations until we're forced to really confront reality, which I think we finally have been.
So we had another few questions. So Trevor Austin was asking about Planet 9's composition, whether it would have any unique geological effects due to its distance from the sun. And kind of related to that, we had a few questions from Osvaldo Gonzalez and Sebastian Rojas Espina asking about asteroid mining. I mean, so for example, you know, is there, if we know the composition of these asteroids, is there a possibility to mine? And I quite liked the way Osvaldo worded it, though he worded it in Spanish. Can we calculate the orbits and how the orbits would be affected by the mining, or are we simply children playing with matches?
Okay, so I know the answer to the first question. The second question, I'm not so sure I'm going to be so good at, but I'm going to answer the first one first, which is about the composition of Planet 9. I know the answer because the answer is I don't know. What we know about Planet 9 is that it's about 6 times the mass of the Earth. Other than that, we only know its gravitational effects. So Planet 9 has the exact same gravitational effects if it's a rocky planet, if it's a gassy planet, if it's a large hamburger, or if you can sometimes read on the crazier sites around the internet that maybe it's a black hole. I mean, sure, it could be a black hole. It's not a black hole, but yes, a black hole would work just as well as anything else. So we don't know, but again, the fact that we don't know doesn't mean we're not willing to speculate. It's what we do best. So if you believe my hypothesis that I started with, which is that it's formed around the Jupiter-Saturn region, that it's probably a lot like Uranus or Neptune, which means that it's mostly a ball of ice, of sort of fluidy ice with a small gas envelope around it. If you took Uranus or Neptune and moved them out to the distance that we think Planet 9 is, the main effect that would happen is that it's so cold that many of the gases, the trace gases in the atmosphere, would freeze and form clouds much lower. So you would just see this nearly uniformly white ball of gas. The best theories these days really predict that, a uniformly white ball of gas. It'll be interesting to see. Again, I'm not sure I believe our ability to predict these things very well, but it'll be fun to see what it really looks like. Asteroid mining, I have to tell you, I'm not convinced it's ever going to be a very viable thing to do. People love it, love the idea. People love the science fiction. If it's ever viable, I think the most viable thing to mine is going to be water from asteroids, and that will be useful if we ever have a pretty major spacefaring economy. You can use water as fuel. The metals, the minerals, it's going to have to get to be really expensive to get them on Earth to make having it happen on asteroids a very profitable thing. People are thinking about this. People are trying it, but I often think it's because when people get to be billionaires, they start to think crazy things, and then they think about space, and then their brains go a little bit crazy. So I really think that most of the space mining, Elon Musk wanting to fly to Mars, is really just kind of space enthusiasm, not very connected with reality. But maybe I'm wrong. Maybe it'll all happen.
Thomas, do you want to ask your question while I filter through?
Yeah, so there is, things are bubbling up here in the same direction in the Q&A. So this is a statistics game right now, right? So yeah. we entered the regime where really numbers and number densities, especially as a function of mass, right? The density distribution functions of these objects make a huge impact on the model, whether it's viable that there is one planet out there, there may be, many bodies out there, how these lower mass bodies are essentially perturbed. If we then go out and look for them, and you probably know that there is the OSOS survey and is discovering more and more of these things at those pericentric distances, how do these new measurements of the orbital parameters fit in now into this picture as we populate more, basically with lower mass bodies, these areas do? Yeah,
so I would say that the like that one plot I showed you includes objects from this one survey being done, AUSOS it's called, by the Canada-French-Hawaii telescope on Mauna Kea. The other big survey that's been finding some object is the Dark Energy Survey being run there in Chile. And then there are a couple other individual people doing surveys too. All of the surveys are consistent with the existence of this planet. The problem is the people people sometimes interpret their own surveys wrong, either on purpose or not on purpose. I can never quite figure out what it is. All of the individual surveys are too small to say whether the Planet 9 is real or not. The individual surveys don't have enough statistical power to see anything. So sometimes when people don't have a big survey, they say, well, our survey doesn't prove that there's Planet 9. And the answer is, right, your survey is too small. That's why we use all of the data instead of just one of these small surveys. So this has happened with ASOS. They have papers coming out that have been out that say, they say it wrong. They say, we have evidence that there's no Planet 9, when in fact, all they have is no evidence for Planet 9 because they don't have enough data. Dark Energy Survey kind of does the same thing, but if you take all the data in aggregate, calculate the biases correctly in aggregate, the aggregate surveys are, the probability of this clustering that we see in the sky being due to chance and observational bias, we've calculated as something like 0.2%, I believe. But you only get that low probability if you actually use all the data. So somebody could go and do a new survey and double the amount of data, they would find the same statistical power. But the small surveys individually aren't going to do it. And strangely enough, the people who do these surveys don't seem to understand that, or I think they maybe get more press if they kind of say, there's no Planet 9. So maybe they choose to not understand that. I'm not quite sure. It's a little strange. Yeah.
So I mean, there is a bias assessment, of course, an observational bias, where
Yeah.
we look at, right, how our selection function in the sky affects our
Absolutely.
modeling, right? So hopefully someone is taking all the data out there and is putting it together and making it consistent.
Yeah, that's me. So we take all the data,
yeah.
and we calculate the biases for the entire ensemble data set in I'm going to say, a very clever way that I came up with. I'm very proud of this. Read the paper; it's pretty good, and I think it works. So we some of these other surveys calculate their own biases. We then use our method to show that we produce the same biases they have. When we take all the biases together, the idea is that, like, we're finding all these objects because we only look in one direction, which is just a ludicrous idea to begin with. I mean, it's these surveys that have been done really are much more uniform on the sky than any one survey. The problem is the small surveys look only in one or a small number of directions. So the small surveys are highly biased, and they then interpret that as everybody's biased. Everybody is biased. That's why you take the entire ensemble, which people should be doing.
Yeah. So what's the next step in this, LSST?
I should have said, there are three ways that this is going to be found, I think. So this is going to be found either by somebody going through archival data and connecting the dots on something that's moving across the sky, and we're working very hard on that. We're doing a reanalysis of the Pan-STARRS data because I think that's the best all-sky data set that goes moderately deep. We'll see, particularly in the galactic plane, it could be there. That's possibility one. If it's a little fainter than the Pan-STARRS limit, then it could be found in these smaller scale surveys that individuals doing. We're kind of closing down our Subaru survey. I don't think that's actually the most profitable way to do it. So we're actually not doing any more observations at Subaru, but some of the other groups are still doing that. That's the second way. And if neither of those work, and they really should work now or give up, the one thing that's going to find it can't hide. You will not be able to hide from LSST, from the Vera Rubin telescope. The northern locations are a little further north than the standard survey is going to go, but I'm pretty sure that we will happily tweak the survey to go find Planet 9 if it hasn't been found at that point. There's no way to hide it from Vera Rubin. So basically, I don't know what the latest on first light for that telescope is and when the first survey is going to happen, but within a year or two of the survey going on, we'll find it. So 2025, I kind of feel like there's zero chance it can be hiding by 2025.
Okay, so should we take a few more from the Q&A, Evelyn?
Yeah. So I've picked out another one that I keep losing because it keeps jumping up the sheet. Alan Maury, what would be for you the difference between a dwarf planet and an asteroid? So he says he's never found a correct definition himself, and at what level of diameter, mass, a given object can be called a dwarf planet.
Yeah, so I will answer that question with the preface that I think the term and even the concept of dwarf planet is a pretty stupid one. So you're welcome to just throw it away and never think about it again in your life. That's the easiest answer. I'll tell you why that term exists. It was a desperate last-ditch attempt to get Pluto to be a planet again. So the people who were super pro Pluto thought that if they could get that term dwarf planet attached, that would have to mean that Pluto was a planet because it's a dwarf planet. That vote got shot down, but we got stuck with this dumb term. So, okay, here's what it means. All it means is anything that's round, that's not a planet, is a dwarf planet. The problem with that is that there are, where do you draw the line? There is no real, very strong dividing line between the things that are round and the things that are not round. You can, if you really care, which again, I think it's not worth caring about that much, but if you really care, you can look, for example, at the icy satellites of the solar system, because most of these dwarf planets are going to be ice balls. If you look at the icy satellites, at around 200 kilometers in diameter, things go from being kind of not round to kind of round. So as a useful rule of thumb, you could probably say that things bigger than a couple hundred kilometers are probably dwarf planets. The interesting thing is that by saying that, you've learned nothing interesting. This is why I think this concept is just doesn't get you much. So yes, it's kind of round. That's what you've learned. So that's my answer. Maybe not a very satisfying answer. I'm just not a big fan of the whole term. But it's funny because before the whole vote came out, we had a word for those kind of big, iconic, round things in the outer solar system that were not planets. We called them planetoids. Planetoid, planet-like. I actually thought that was a much better terminology. I'm sad that the desperate Pluto huggers hijacked the terminology and turned it into one that's not as good.
I like the question here by Peter Broughton, which is pointing in the direction of, can we use any other diagnostic?
Ooh.
Right? Like, do we have any sensitivity in anything else in the solar system?
Such a good question.
Can, suck out information about Planet 9 in addition to what we already have.
The answer is emphatically yes.
Yeah, so let me finish the question here because it makes a really cool point here. So Comet Halley, right, is being monitored for quite some time. Unfortunately, it doesn't go probably far enough out, right? Aphelion, but there must be other well-measured distances, right? That we can.
So the answer is yes. Comets are tough because comets, when they come close to the sun, they get jets, and then their orbits modify, and so it's really hard to carefully figure out where they are and predict where they're going to be exactly again at the level that we need. So they're tough. The best thing to date that anybody has come up with is really good, and I like it, but it's been a little hard, which is one of the best measured distances in the solar system over a long period of time is the distance from Earth to Saturn. And that's because we measured the location of the Cassini spacecraft as it's in orbit around Saturn for 10 years. And it's not just a single measurement. Saturn then is going around the sun, so we're measuring it as Saturn goes around and as the Earth goes around, and so we're measuring it at all these different locations. Planet 9 will have this tidal force on everything in the inner solar system. The Earth moves by about 10 meters every year because of Planet 9, back and forth. It's a little too hard to measure. Shockingly, we can't measure that because we don't know the masses of asteroids well enough, and asteroids fly by and jiggle the Earth even more than that in unknown ways. But going all the way out to Saturn, there's a much bigger effect. And so nearly the day we published this idea of Planet 9, this group in France published a paper doing an analysis of the Cassini distances and came up with a very strong prediction of where Planet 9 was. And it turns out that there was some technical problems with the paper that only came out like 6 months later. They've gone back and redone the analysis now. It's very complicated analysis because you have to, it's not just where Saturn is, it's where the Cassini spacecraft is. The Cassini spacecraft is maneuvering to go around moons, and you have to know where the moons are. And so there are the most aggressive arguments I've ever heard in a scientific conference were one that was discussing this concept, and it was about whether you know the position of the Cassini spacecraft with respect to the center of Titan, and you don't know. Like, I certainly don't know. So I have a hard time knowing what exactly, how well to believe these data or not. But anyway, they have a paper coming out moderately soon that has a prediction of where Planet 9 could be, and with no information from us, they just made up an entire prediction of where it should be. I'm going to share my screen again just because it's just too good. I might go back. I'm going to go back. There I am. Okay, their prediction is that it's right there. It could have been anywhere in the sky. We didn't tell them this is the orbit of Planet 9. Look here, this is perihelion, this is aphelion. They just predicted where it was, and that's their prediction. So
It's hiding in the perfect spot.
so maybe that's, so I mean, again, this is a difficult analysis, the details of which I understand poorly. But maybe.
Very interesting.
I have a couple of questions again from the audience. So there's two very similar ones. So Ariel Gutierrez has asked, what is the probability that Planet 9 simply doesn't exist? And connected to that, Alvaro Ribas has asked, what fraction of the probable parameter space for Planet 9 has already been ruled out by the observational campaigns? I mean, what fraction would make you start thinking that it's more likely that Planet 9 is not really there? Yeah, so good questions. I would say that the probability that Planet 9 doesn't exist is awfully close to zero. I might be a little biased about that. But again, if we think through just the stuff that I talked about, it explains, it was designed to explain the alignments of these objects. Okay, so it doesn't get credit for, gets a little credit for explaining what it was designed to explain, but that's what it was designed to explain. With no extra parameters or addition or anything, it accidentally explained the distant perihelion of Sedna, the fact that Sedna and VP had those distant perihelions. It accidentally explained the tilted objects that nobody had ever come up with an explanation before. It accidentally explained those other close-in objects that are also tilted that nobody had an explanation for. It predicted that new observations would come out that would also be aligned in the same direction. Those are pretty good. So if it's not real, every single one of those other things needs its own separate explanation, and that's very dissatisfying to me. What I think is good is a planet is such a not surprising thing to have at these distant locations. We see other stars in our galaxy that have planets like that out there. It's just such a natural explanation that it seems unlikely to not be real. So let's get to that question about parameter space. Let's look at that parameter space. You can see it right there. Here's your parameter space. So I would say at this point we have ruled out. I have an actual number, but I don't have it with me right this second. I would say that we've ruled it. Oh, and there's even another one. We can go to that one. At this point, we've ruled out, I think, something like 70% of the parameter space. And the parameter space that we ruled out was the easier stuff, the stuff that was fainter. The stuff that was brighter, the stuff that was closer to the sun, and we ruled that out pretty well. It means you would like to find it at that moment when you have ruled out precisely 50% of parameter space. That would make you a very happy person. Actually, you would like to find it before you even start to rule out parameter space. That would make you even happier. I am sad that we've ruled out 70% of parameter space and not found it. As we continue to rule out more parameter space, when will I get worried? Well, I'll tell you, I'm worried.
I still think that there is 100% chance that there is a planet out there, but I'm sufficiently worried that every once in a while I sit down and I think, what is it that what could be wrong? There's one thing that's easily wrong, that can make it a lot harder to see, and that's that we don't actually know the albedo of Planet 9, how much sunlight it reflects. So we're having to make that up in all these predictions. We make it up based on these models that people tell us are true, that it's really bright and reflective. If it's not really bright and reflective, all of these curves that you saw about how bright it is and how much is ruled out, all those curves move up to fainter. And we really do need the big telescopes to have a chance of finding it. When I lose sleep at night, that's the thing about which I lose sleep. I hope that we find it in the next 30% of parameter space, and it's not just that it's faint, but I will let you know.
Do you have any final questions from the panel? I will take that as a no. So yes, thank you very much, Mike. That was a really fascinating talk. So yes, to everyone, thank you all for joining us today for the talk, and thanks to Mike for taking the time to tell us about your work. All the talks in the series will be added to the Astrofísica UC YouTube account in the coming days, both with the English and the Spanish soundtracks. These videos also have a higher quality than the live stream. I know, for example, some of the videos were a bit jerky on my screen, so that'll be corrected in the videos on YouTube. So our next scheduled talk will be on the 10th of July, and we'll have William Borucki, who will be telling us about his work on the Kepler mission. And so there's nothing left to say except to say thank you again and to see you all next time.
Thank you, everybody.
Thank you. Take care.